As was announced, my talk will be about the minimum description length principle. Probably I should make a slide with motivation. Let me say sorry, because my talk will not be about some AGI applications of the minimum description length principle, and my motivation is follows. Probably most of you knows about Kolmogorov complexity and its usage in AGI. 2 years ago, for example, Markus Futter has a tutorial on universal intelligence, and today we heard a tutorial which also mentioned about Kolmogorov complexity. So it's not a question that Kolmogorov complexity is used in AGI, but the problem is that it is used mostly in theoretical investigations or probably in toy environments. And there is an opinion in quite large part of AGI community that Kolmogorov complexity is not that useful. It's simply some theoretical, uncomputable idea that actually has no relevance to practice. But for myself, I came to using the minimum description length principle and Kolmogorov complexity from practice. And I'm sure that it is a very practical idea, and it is very useful in practice. So my talk will be more about this narrow AI applications of the minimum description length principle, and I will not be talking about some basics of the MDL, because I'm sure most of you knows probably even more than me about this, but my motivation is to show you that this principle is really useful both in theory and practice, and the way to AGI lays in bridging the gap between narrow and universal induction methods. For me, everything started approximately 20 years ago when I was an undergraduate student, and I began to work in a team solving computer vision and image processing tasks, practical tasks for different customers. And my first task was connected to aerospace image matching. Back then, I had quite limited knowledge in this area. So imagine that you don't know anything about image matching, and you need to find corresponding points on two images. So what is the most natural solution? I guess that most of naive developers will try to invent something like least square error based methods or correlation based methods. So we should put one image on another and shift it and find such positions which yield a minimum of some natural difference measure, such as least square errors. And there is some techniques which can help to calculate this measure much faster. For example, we can calculate correlation field via Fourier transform, and it's quite practical. One can think that the main limitation of the correlation-based methods is that they deal only with shifts, but there are extensions of these methods, for example, based on Fourier transform, which can deal with more difficult types of spatial transformations, for example, rotations and scales. And actually you can use something like block matching in order to compensate even more general types of spatial transformations between two images. And then you can construct a displacement field and match images which are transformed by a quite general type of transformation. So is this the solution of the mentioned task? Actually no, because if we look at images taken from different types of sensors, for example, optical, infrared, or synthetic radar aperture images, or images taken in different seasons, especially if you have a lot of snow during winter and this snow is absent in autumn or summer, then it will be quite difficult to match two images with such different distributions of brightnesses. And if you try to match such images as common images and, for example, digital maps, then correlation methods will also not work. So it seems that the problem is in nonlinear transformations of brightnesses. And back then I found a dissertation, a PhD thesis devoted to image alignment by maximization of mutual information. This was the first time for me to encounter powerfulness of methods based on information theory. For example, if we have two signals, two noisy signals, and they are connected with each other by some nonlinear transformations, then correlation will faster degrade, while mutual information criterion will give us a very sharp extremum. So we can use this criterion to match images which are transformed by very nonlinear brightness transformations. Well, unfortunately, even if this is a very beautiful approach, it doesn't work for example, matching images with digital maps, and it is quite slow because we need to overlay one image over another with different parameters of the spatial transformation and construct histograms of mutual distributions and calculate mutual information, and there are no fast methods to do this like for correlation when we use a Fourier transform. So it's not very practical, but the idea itself is quite beautiful. Instead, in practice, we used structural matching methods. Basic idea is to extract contours and approximate these contours with some structural elements, and then try to find correspondences between these structural elements. We used Hopfield-Tank neural networks for this, and tree search based methods which appeared to be more general because we managed to match images transformed by rotations and scales while using neural networks, but with tree search it was possible to match images transformed by affine transformations or even projective transformations. Okay, well, using structural matching methods, it was possible to match images of the shown types. But I wasn't satisfied with with this approach because of its heuristical nature. And many other questions for me arise. For example, how to estimate quality of structural descriptions, how to choose the group of transformations if it is not known a priori, how to construct contours and structural elements optimally, and so on. Indeed, if one tries to use minimum square error criterion in the case of image segmentation, he or she will get over-segmented results. Indeed, the more number of segments we construct, the less average error will be, and these results are absolutely inadequate. So we need some heuristic criterion to stop our region merging or division process to choose the most appropriate number of segments. Actually, it is quite a widely spread problem, and it is well known in the field of functional approximation. For example, if we try to construct polynomial approximation of a given number of points, which are noisy points constructed by some process. And we will try to minimize minimum square error. In this case, we again will obtain overfitting results. So we will obtain the polynomial with the maximum possible degree, because the higher degree of the polynomial, the less the error will be. And this result will be inadequate because prediction of made by this highest degree polynomial will be quite worse. Again, here information theoretic criteria can help. I found some works on structural matching based on the mutual information criteria. So there were some scientists who generalized mutual information criteria for matching structural elements, and there were some works which used information theoretic criteria to choose the most appropriate number of segments, for example, in the image segmentation task, and so on. And I encountered a lot of works devoted to the minimum description length principle, which was used loosely in such practical tasks. And such loose formulation of the minimum description length principle states that the best model or the best description of the data is the model that minimizes the sum of the description lengths of the model and the description lengths of data encoded by the model with the help of the model. Actually, on this level of strictness, the minimum description length principle is very similar to the bias rule. Indeed, if we take logarithms from the both parts of the bias rule, we will obtain mostly the same formulation as the minimum description length principle, because we will have some part which corresponds to the description length of the model, and some part which corresponds to the description length of the data encoded by the model. But the minimum description length principle was more convenient for me, because if we use it, then we don't need to specify prior probabilities explicitly. Instead, we simply say, let us code our model in the following way. And it is much more natural for a developer to imagine some coding scheme for model parameters and to calculate its description length instead of explicitly specifying prior probabilities. But the difference here is not very much. So if one applies such a loose definition of the minimum description length principle in the mentioned tasks, then it will be possible to solve the mentioned problems, the problems of overfitting or oversegmentation. For example, here we can say that let's encode model parameters with some precision, and then we can calculate the description lengths, and let's encode deviations of our data from the model. And then these deviations will constitute some additional description lengths. And the best model will be the model which gives us the best trade-off between the model complexity and its precision. So here we will easily get the best solution, and this solution will not only have the minimum description length, but it will also give us the best prediction precision. The same can be obtained, for example, for the image segmentation task. Here you can see the number of segments, and when the number of segments is large, then the total description length is high. And somewhere in between the less number of segments and the most number of segments, we have some compromise between the model precision and its complexity. The same holds, for example, for the task of construction of structural elements based on contours. For example, here we have two borders and two contours extracted for these two images. And if we use minimum square error approximation, then we need to apply some threshold on the MSCR value. And if this threshold is too high, then we will get one segment here and one segment here. And if it is too low, then we will get appropriate numbers of segments here, but we will get also several segments here. But the MDL criterion helps us easily distinguish these two cases, because here if we increase the number of segments, then the precision of the model greatly increases, and this increase of its precision is greater than increase of its complexity. But in this case, increase of complexity of the model doesn't help us to considerably decrease the description length of data encoded by the model. So such loose application of the minimum description length principle helps us to solve such problems in practice. And using this information theoretic approach, we were able to construct an image matching method which was able to match images taken from different seasons or different types of sensors. And actually, it's not quite easy task. But, okay, so here is some examples. We can even match images with digital maps, or images, optic images with synthetic radar aperture images. And if you think that this task is quite specific, if you think that this task is quite specific, then we applied the minimum description length principle in other tasks, for example, image matching task in the case of 3D scenes and dynamic environment. Probably many of you know about feature-based matching. Actually, feature-based matching, such methods as shift or surf will not work in these cases because local features will be very different. They are not invariant to changes, to such changes of local brightnesses, so they will not work. But actually, in such cases, they can work, but there is still room for applying the minimum description length principle. For example, here we used it to choose the most appropriate number of fundamental matrices, because in the case of multi-body motions, each body has can be described by its own fundamental matrix, and in the case when we don't know the number of moving bodies, then we somehow should determine this number, and the minimum description length principle again helps us, because more number of fundamental matrices we used, less the zero with which it maps key points from one image to another, but at the same time the model complexity increases. So again, we will be able, by using the minimum description length principle, we will be able to find a compromise between model complexity and model precision. So again, it's quite a practical example. Back then I found many applications of the minimum description length principle applied by different authors to improve different methods. And I was fascinated by this wide applicability of the minimum description length principle, so I even wrote a book on its applications, unfortunately only in Russian. But indeed, there are many applications of the minimum description length principle, and I mentioned only one our application, but we also have much more applications. These applications cover not only pattern recognition and computer vision tasks, they also are very characteristic for symbolic domains, for example, for learning grammar. Actually, there is a problem of learning grammars when we have only positive examples, but again, the minimum description length principle helps to distinguish between solutions of different complexities and choose the most adequate grammar among many other possible solutions, even if we have only positive examples. Okay, it's quite useful, and I was a fan of the minimum description length principle, its practical applicability, but again, I wasn't fully satisfied with the way it was used, and more questions arose for me. So the main question is how to define coding schemes within which the minimum description length principle is calculated, because in practice these coding schemes are defined fully heuristically. It's quite convenient to define them in such a way, but it leads only to slight improvements of existing methods, but not to developing new, more powerful methods. So is there a way how we can overcome this arbitrariness? And then I discovered for myself that there is such a idea as the Kolmogorov complexity. It was approximately 10 or 11 years ago, and I discovered works of Schmidt-Huber, Solomonov, and Hutter. And I found that the basic idea beneath the minimum description length principle is algorithmic information theory. So I will not go into detail regarding this theory. I only say a few words how Kolmogorov complexity is connected to the minimum description length principle, because one of the main ideas of the minimum description length principle is two-part coding. So we can move from Kolmogorov complexity to the minimum description length principle by two ways. Either we can separate the program and its input data. So then we will say that our program is the model, and its data is the description of the observation data encrypted by this model. So we will minimize the sum of the length of the program and relative Kolmogorov complexity of the observation data given this program. Another way is to consider stochastic programs, stochastic Turing machine, and in this way we will get the description length of the program, and actually the probability that this program will generate this data when it is run on the stochastic Turing machine. The second approach actually is very useful when we are talking about probabilistic programming languages. I will not include this part in my tutorial because we have a poster devoted to the usage of the minimum description length principle in optimization queries in probabilistic programs. So if anybody is interested in this part, we will talk about this later. Okay, so the main idea here is that the universal Turing machine defines the universal model space. I guess all of you or most of you know about universal prediction proposed by Ray Solomonov, and it extends the idea of Kolmogorov complexity because Kolmogorov complexity can be used to choose one best model, but algorithmic probability can be used to make best predictions by averaging over all possible models. And it can converge much faster to the best prediction, and actually if we use this approach within AGI, within intelligent agents, then we cannot use simply one best model because in this case we will face the problem of lacking of exploration. So this approach will lead us only to exploitation of the present knowledge. So actually there is some difference between Kolmogorov complexity and Solomonov probability in terms of intelligent agents, and actually we had a paper 3 years ago on this topic, so I will not go in details here, but I think that it's worth mentioning that there is such a thing as Solomonov universal induction and prediction. So what I found in universal induction or prediction methods, it's a universal model space. So Jose, in his tutorial, said that AGI is a system which can solve such problems that it hasn't encountered yet, right? So if we construct narrow methods, we always construct them to solve some specific problems. But universal methods, they can solve any problems. If we are talking about induction or machine learning, we are talking about some specific statement of these problems, but well, it's another question. So if we try to solve the problem of induction by universal methods, we will be able to, for example, to predict numbers of pi or something else. So any computer model is presented in the universal model space, and any problem for prediction, for example, can be solved using by these methods. Of course, I was a practitioner, and I clearly saw that these methods are not practical. They cannot be directly applied for solving my own problems, but they answered my questions which arose from practical tasks. And again, from Solomonov's works, I found out that practical problems, such practical problems as overfitting or overlearning have their deep counterparts in a theory and even philosophy of inductive inference. For example, there is a well-known Grue-Emerald paradox, which consists in the fact that we cannot distinguish between two hypotheses which are supported by the observation data equivalently. So, for example, we see that all emeralds are green, but we also can propose a hypothesis that they all are green until some date and blue after this date, and we have no direct evidence for choosing the first hypothesis instead of the second one. And universal priors, simplicity priors can solve this problem for us. And this is actually the same problem as overfitting, but here it is shown in some pure form. So we don't need to think that there is some mystery beneath overfitting, overlearning, and so on, but there is one common problem which goes from some deep theoretical foundations. So for me, theory of universal induction answered some questions which were not quite obvious in practice. Indeed, if you take some book on practical machine learning, some handbook on pattern recognition, and so on, you will see that there will be a lot of talk about the problem of overfitting and overlearning, and there is no clear answer from where these problems come, because you will find some techniques such as cross-validation, some learning curves, biased methods, and so on. But there will be some practical recipes about how to deal with these problems in a narrow sense, but there will be no answer from where these problems come. And this is quite surprising, because the answer is in the algorithmic information theory and the theory of universal induction and prediction. Also, there is some mystery about neural networks and no free lunch theorem. In practice, many researchers on some stage of their development, they try to construct some universal method for pattern recognition or something like this, and they came up with something which is called yet another classifier. They are trying to claim that they invent some general method, but it appeared that it is not quite general method. It works better in some cases, but it works worse in other cases. And because of this, there is no free lunch theorem, which simply tells that no method can work better in all possible cases, and so on. But the theory of universal induction clarifies all these questions. It tells us why narrow methods are narrow. What is the problem? So the problem is that they use non-universal model space, and it tells us how in principle it is possible to overcome this problem. So no free lunch theorem is actually not true. Well, again, I will not go in detail, because Markus Kutter also mentioned about this in his tutorial 2 years ago. Okay, and one thing that especially shocks me is about recurrent claims that feed-forward neural networks are universal approximators. Again, it's not really true. Well, we can approximate, of course, Kolmogorov theorem is true, and its implications are true, and we can approximate any smooth function in some interval with composition of such functions and so on, but it is not true in sense of machine learning, because approximation is not what we want. We want prediction, and it's like epicycles, and when we observe planet motion with more and more details, we add more and more epicycles, and we can describe the motion of planets with better and better precision, but we cannot predict parameters of new epicycles with this approach. But if we use model from a large model space, and we manage to develop Kepler's model of solar systems, then we will be able to predict positions of planets with much more precision using much less data. So, well, universal induction simply helps us understand all these issues. But, well, there is still a gap between universal and practical methods, because on this level, universal induction is absolutely impractical. It cannot be applied directly to practical tasks, and this is main argument against it in the AGI community. Well, for me, as a practitioner, it helped me to understand many things, but, well, indeed, how can we overcome this gap, and do we need to overcome this gap, or universal induction is simply some abstract concept which cannot be realized in practice? I believe that it is not simply an abstract concept, and we really need to try to bridge this gap. So one of the most obvious ways which can be used to try to bridge this gap from the side of universal methods is to choose a universal Turing machine, to choose such a machine. Well, actually, if we choose appropriately a reference machine, then we will get an inductive bias which can help us to learn appropriate models quicker. So this is quite obvious idea. It was mentioned in different publications, starting from Ray Solomonov and some publications in AGI proceedings. But actually, it's not a complete solution. It's a small step to bridging this gap. But can we do something else? Let's go back to practice. As I mentioned, when we were working on image matching methods, structural matching methods, heuristical structural matching methods appeared to be more efficient than information theoretic based methods which work on the level of pixel brightnesses. And even if we use information theoretic methods for constructing structural descriptions, then we will encounter some cases in which they don't work. For example, if we consider such images which have smooth gradients and apply the methods which I briefly described, then we will get as segmentation results something like this. So these are essentially incorrectly segments on images. Of course, we can develop some more complex models for describing image contents. For example, we can approximate each region in the image using its own regression function, and we can use, for example, polynomial approximation and Gabor wavelets or something like this. And in this case, we can obtain much better segmentation results, even when we don't see contours. These methods can give us borders between different regions of images. So we can improve, we can greatly improve our results, but by not using information theoretic criteria, they are already there, but by using different classes of models. And actually, in computer vision, there is a fundamental notion of representation. Well, it was used, I guess, for a long time, but it was formulated by David Marr as some formal system which can describe how to generate objects which are to be described. And in image analysis and computer vision, there is also a well-known structure of different types of representations. For example, representations which are characteristic for raw representations, low-level representations in the form of some functions or stochastic processes, contour-based representations sub-symbolic representations, structural representations, and so on, up to the knowledge-based representations. And actually, in image matching, we also can distinguish between different methods based on the underlying representation. So there are image matching methods which work on low-level representations, for example, Fourier-based and mutual maximization of mutual information-based methods are low-level methods. There are contour-based matching methods, structural-based matching methods, and so on. So we can see that the type of representation is a separate component from the criterion. So we can separately deal with the criterion and with the representation, and it is the representation which gives our method a power to deal with more and more complex cases. So it is quite interesting if it is possible to somehow formalize the notion of representation. Because again, in computer vision, they are introduced rather heuristically, and one can see that representations which are used in every method of image processing, computer vision, and actually speech recognition, and any method of pattern recognition and so on, they are very similar to heuristic coding schemes which are introduced in the loose application of the minimum description length principle. So the question is, based on what criterion and from what space we can choose our representations. We can look at machine learning pattern recognition methods which actually construct representations, and we can also apply the minimum description length principle there. For example, we can try to learn polynomial decision functions and to construct new features. We can try to solve the problem of clustering and choose the most appropriate number of clusters, and so on. So we can use the minimum description length principle together with pattern recognition methods in which representations are actually constructed. But actually in these methods, again, we use some heuristic coding schemes. So can we find some correspondences between representations and some notions in algorithmic information theory? Well, if we consider our tasks of induction, machine learning, pattern recognition, computer vision, image processing, and so on as the mass induction tasks, then we will see that we have a number of entities, for example, images or patterns, and we construct a method which deal with each of these instances independently. Then we should state the mass induction task. And if we consider it in the context of universal induction, then we will see that if we solve each instance of our task using universal induction, using universal priors, then we will obtain much higher description length, much higher Kolmogorov complexity of the sum of Kolmogorov complexities of individual tasks than Kolmogorov complexity of their concatenation. So actually we need to derive some mutual information from these data entities, and we can call this mutual information contained in these data entities a representation. And we can construct something like representational minimum description length principle. Within this principle, we can say that the best model of the data is the model which gives us the minimum sum of the description length of the model itself described within the given representation and the description length of our data described within this model. So the main idea here is that we describe models within some representations. And then we can say that the best representation for some set of task instances is the representation which helps us to minimize the sum of description lengths of these data entities within this representation if we construct best models for each such data entity. Here, well, actually there are different generalizations of the loosely defined minimum description length principle which go from statistical learning theory, but they don't explicitly say from which space we should take our probability distribution. So, well, I decided not to add slides about this theories, but they could be quite useful in practice, but they don't try to bridge the gap between universal and practical methods, so I'll skip them. But when we are talking about the representational minimum description length principle, we say that for each narrow method, we can, for each specific task, we can try to construct a representation which can be taken from the Turing complete model space. So, using the RMDL principle, we can extend our narrow methods. So, if we use the minimum description length principle to specify criteria for model selection to overcome overfitting and so on, then by using the representational minimum description length principle, we can try to extend our narrow methods. For example, we can automatically choose between different handcrafted representations, or we can generalize some narrow method by introducing parametric family of representations in which this method will be represented by one particular case, and try to learn representations from this specific parametric family. There are some examples how we applied our RMDL principle in practice. For example, we tried to generalize the neural networks by introducing additional components in them, and tried to apply it in the problem of time series predictions and robot control. And we saw that by using the RMDL principle, we can quantitatively compare different neural networks formalisms for different problems, and criterion can compare these methods. And even if such criteria for comparison as mean square error doesn't work, it can show us, for example, that some prediction probably not precise but structurally correct. For example, here is a prediction which has the same structural features as a real data time series, but it has quite large errors. But this structural correctness is not reflected in the MSCA criterion, but it can be reflected in the RMDL criterion. Or, for example, if we have some images from a new domain for which humans don't have some heuristic or natural understanding of what representations should be used, and we cannot say that these representations should be better because we know this from our own visual experience. In these cases, we can again apply the representational minimum description length principle to objectively compare different representations for a new kind of images. For example, for optical coherent tomography images for which we actually don't know what representations should be. And again, we can objectively compare quality of representations using this criterion. It can be used also in feature learning and so on. One interesting implication, well, I have not too much time, so I'm going faster. One interesting implication is multi-level image analysis. So using information theoretic criteria, we can say, for example, that to construct the most appropriate image description on a higher level, we should not only construct step by step good descriptions on previous levels, but we should optimize the total description lengths, which should be considered as a sum of description lengths on all levels, and this can help us formalize in terms of information theoretic criteria such a fundamental effect of adaptive resonance, which is usually formalized in neural networks and is one of basic ideas, for example, in some deep learning networks, some advanced deep learning networks, but this effect can be considered in terms of information criteria. It leads to very interesting results. For example, if we construct image segments or structural elements in a one-way direction without corrections of structure of descriptions, then we will get quite noisy contours and quite noisy segmentation results. But if we try to optimize total description lengths using adaptive, some sort of adaptive resonance, then we can correct segmentation results based on structural description results. Or we can even correct structural description results based on matching results, because we can state our image matching task as a task for constructing minimal mutual description of two images which are to be matched. So after matching these two images, we can improve descriptions of these images. And this is useful because if we can successfully adjust two descriptions of images in such a way that they will be more compact, then our hypothesis of how these images should be aligned is correct. And for some incorrect hypotheses, we will not be able to minimize mutual description length. So this idea goes further. So as we can see, one of the fundamental problems is to learn representations, because representations are central in narrow methods to be efficient to solve large sets of problems. And if we want to further bridge the gap between narrow and universal methods, we should somehow we should somehow learn these representations. Actually, such methods as deep learning are successful because they extend the set of possible representations which can be learned. And actually they also resemble minimum description length principle or representational minimum description length principle because one main idea behind deep learning is that if we use many layers, then we can compactly represent some function, much more compactly represent some function than if we use only one layer. Actually, there are some theorems that we can get exponential decrease in size of representation as a size of neural network. So actually, it can be considered as a particular case of the minimum description length principle. But we also can say that deep learning, I say probably not every deep learning method, but deep learning based on feed-forward networks are not universal because it works not in a universal model space. So, well, if we have time, we could talk more about this because there will be some interesting talks in this conference about limitations of deep learning, and these limitations can also be seen from the perspective of the universal induction. But okay. We have unfortunately no time for this. The question is why these methods are successful? Because they extend the possible set of representations which can be learned, and they are still efficient. So to bridge the gap between universal and practical narrow methods, we need to understand how to make methods, how to deal with the problem of search, of course. So we have some area in which practical methods and universal methods coincide, in which they can support each other, and this is I think the next step that should be done in order to further bridge this gap and to achieve both practical and universal in some sense methods. And here one my colleague proposed an interesting idea based on specialization. So previous speaker also mentioned specialization, but here we are talking about specialization in a strict sense as a construction of efficient projection. So basic idea is that universal methods should not it should not be one general method that is uniformly applied to every kind of problem. Instead, we should construct such a method which automatically builds efficient projection of the universal method on the problem set at hand. Well, I will not go in details here, just I'll say that we can formally consider the problem of specialization of universal induction, and we had a talk on this last AGI conference, and it yields us some useful results, but the problem is far from being fully solved. So I guess we should have 13 minutes for questions, and on this I will end my talk. Thank you for attention. questions? Yes, please.
MDL, minimum description length, is simplification of universal prediction. And going in the opposite direction is model algorithm for data regularization. Have you perhaps looked into when maintaining many representations is a win compared to pursuing a best representation?
Well, thank you for a very interesting question. Indeed, we thought about it, and even we have one theoretical paper on it, but the problem of learning representations is itself difficult, and to maintain many representations is much more difficult. So we slightly tried to analyze this problem and showed that it is in principle possible, but right now we have no practical proposals to how to do this in universal settings. Was it your question?
There could be a trade-off between putting less effort into finding the best representation, but instead maintaining a population of representations.
Well, actually, there is another way of how to deal, how to at least theoretically consider these problems. Yes, we also have some similar ideas. For example, in the case of Levin search, in the case of Levin complexity, we take into account both structural complexity and computational complexity. And we were thinking about how to generalize the minimum description length principle and the representational minimum description length principle in a similar way to take computational complexity into account, because indeed we should find a trade-off between computational complexity to find a good representation and information theoretic quality of its representation. Yes, it's a very interesting question, and thank you for asking. I didn't include these ideas in representation, in presentation. Unfortunately, we don't have clear answers right now, but we are trying to develop these ideas also. Yeah.
Hi, thanks for the interesting talk. Have you come across any interesting applications of this in NLP, or is that not an area that you wish to explore?
Well, yes, there are I'm not sure that there are many very different applications of the minimum description length principle in NLP. I saw different applications in grammar construction, and I mentioned about this in automatic extraction of language structure. Unfortunately, I don't deal with NLP problems, so I don't know about many of such applications, but I am sure there are.
Thank you for your excellent presentation. I have a question and a remark. The question is about the no free lunch theorems and the relation with, so I think Solomonov prediction is one of the special cases where you can show that the no free lunch theorems don't apply. So that's nice. But we have recently seen that when we move to interactive agents, let's say universal AI, Hooter's universal AI, we have recently seen that some kind of no free lunch theorems apply. So my question is that I still believe that there's a way to devise interactive agents that don't suffer from the no free lunch theorems, but this is becoming more difficult than expected, or you have a lot of buts, and so it's not that clear as it was for Solomonov prediction. So that's the question. So what can you tell about this? And the remark is that I don't know if probably you are aware about the minimum message length principle was introduced by Chris Wallace 10 years before the MDL principle. I can't resist. I also published some papers using MDL, but I recently, because basically they are the same idea, there's a special issue in the Computer Journal about Kolmogorov complexity where they explain all the details. This is 2000 or 1999. And currently I usually use the expression MDL/MML because I think it's a little bit fairer for, even that I was aware of the MDL principle much before then, some years after that, some people told me about the MML.
So thank you very much for comments. Indeed, I didn't mention the source of this terminology. And indeed, the MDL principle was introduced later than the MML principle, but simply I use the MDL principle not in the sense as reasoning, but something generalized. So something like ideal MDL, which was introduced by Lee and Vitani, so it's not a reference to the resonance MDL principle, but indeed we should say that the idea of MML principle and MDL principle are very similar, and the MML principle was introduced earlier, but because Solomonov algorithmic probabilities were introduced even more earlier, and they generalize both MML and MDL. I think that it doesn't really matter. What about your first question? It's indeed quite a difficult question because we all know that there are some such environments in which no intelligent agent can deal well, like heaven and hell example and so on. I don't like these examples because they are not very natural, and I also feel that there is some statement in which we can say something like that no free lunch theorem for intelligent agents also doesn't hold, but I simply have not yet developed such settings and have not even worked on them. So unfortunately, I think that you have more chances for it. No? Okay. Well, yes, I agree. Well, I agree with you that there should be something like this, but I have no answer yet.
Hi, thanks for your talk. My question is regarded to the encoding schemes, because you motivated the introduction of the universal Turing machines and Kolmogorov complexity by removing the handcrafted encoding schemes. But I wonder whether there's, in the end, you have to estimate the quality of the model, and in order to do this, there has to be this encoding of the training examples in a binary form, so that the output of the, or at least there's some metric has to be defined in order to measure the output of the Turing machine and whether it matches the training examples. So doesn't is the representation problem not still there, or it remains?
Thank you. Indeed, in practice it remains because in practice we don't have right now means to automatically select representations from a Turing complete model space. Because of this, what we can do is to introduce some representation families from which we can select the best representation based on the RMDL principle, but these representation families are nevertheless introduced somewhat heuristically. We simply try to remove this heuristicity more and more, but indeed it still remains.
Any more questions?
Hi, thank you for your talk. My question is, the training for the representation is an offline process. So you do it before you send the system in the Word and let it calculate things. So do you plan to extend your research for an online search?
Sorry, for what?
For an online search of the representations?
Sorry, could you please repeat your question?
So you take training examples, in this case images, and you learn the representation, the best representation is based on this. So when you now send the system in the words, and it doesn't learn new representations for new images it sees in the world. So do you learn to extend it to this?
Do you mean something like incremental learning?
Yes, online learning.
Online learning, yeah, it's also a good question, and it's quite interesting direction to extend our methods, and with colleagues we are discussing the problem of online learning, incremental learning right now. Actually, we also deal with probabilistic programming, and we are trying to do all this stuff in implementation of probabilistic programming, and there is indeed one of what we feel is necessary is online learning. Right now we don't have, again, we don't have complete solutions for this, and we also have some raw materials, but I hope we will have some progress in this direction. But yes, online learning is one of very crucial components of AGI. We were working on practical solutions for a long time, and in these tasks we were required to build a method which will be given to a customer who will use it as a complete solution. So it was not required in these settings, but when we started to deal with AGI problems and problems of intelligent agents, then online settings started to become very crucial, and we started to deal with them. But because it appeared not too long time ago, then we don't have right now a full solution for this.
Thanks.
Okay, I think that's it.
Thank you.
Let's all thank Dr. Potapov again.